Okay, so far what we've talked about in this section that we've been dealing with is we've looked at the two types of basic conductors, either power or communication. Sometimes we can use power for communications, but communication conductors are not used for strict communication instructors. We don't usually use those for power. We looked at a little bit about fiber optics. We'll talk about that a little more. We talked about the best conductors of electricity. We looked at the advantages and disadvantages of copper uh, and and aluminum, also silver and the different alloys. We looked at what calls the resistance of a cable. We looked at the American wire gauge. We looked at the ampacity chart. We looked at the formula, which we'll never use, the different types of cable, and how to calculate the area and all that kind of stuff. But what's really important, of course, is the KC Mills or MCM, which we use for in the US customary for gauging wires. We talked a lot about ampacity. We looked at the ampacity chart for we looked at the standard ampacity chart for the American wire gauge, which not only gives the ampacity in free air. Remember, the temperature is determined by the resistance is determined by the size, the material, the temperature, and the length. So anytime we give a resistance chart or shows ampacity, this is always going to be at a temperature at a certain length. Okay, so the ampacity here would be at 1,000 feet at 20 degrees centigrade. And this is the ohms, and this would be the ampacity. This is the American wire gauge. The other thing that we looked at, of course, was NEC. Now, NEC, what it's done is already dirated or reduced by certain amounts our wire gauges. In residential, the most popular sizes are 14, 12, and 10. These are the ones you'll run into most often. 14 gauge, we use those on 15 amp services or 15 amp breakers. 12 gauge we use on 20 amp services and then 10 amp we use that on like air conditioners and water heaters and stuff like that. We also do use some 8 gauge in housing, but very, very seldom. But it all depends. And this, by the way, shows us how to reduce that. We look at different types of we look at see what insulation was based on. We'll look at that in more detail later on in this slide. The different types. We look at the makeup of a low voltage cable. We look at the makeup of a medium voltage cable. And high voltage cables are also pretty similar to this. By the way, these construction of these cables, the parts of them will be on next week's test. We talked about distribution of electricity, and that's why we talked about on these high voltage cables why they have the semiconductor layer. We went and looked at power point on gain and attenuation, and we also this is where we picked up the decibel. That's going to be on next week's test. You need to make sure you understand that. And we looked at why these communication cables have a certain what we call characteristic impedance, and we talked about impedance matching. Makeup of a coaxial cable. And then we looked at the equivalent circuit of a coax cable, and we talked about it having the same characteristic impedance no matter what the length. And what I have here, of course, is I have a little piece of coax cable. This is RG50. This is RG58 cable. Let's see, I don't know if the camera will pick it up or not, the actual labeling on the cable. I'll try to get it up here. But this is RG58 cable. So RG58 has a 75 ohm impedance. Now the coaxial cables we've already looked at are made up of some unique parts. First of all, we have an outside jacket, and then we have an insulator, and then we have a shield. So I'm gonna draw like this. It's called a shield, but it is a conductor. So, and that's just what it went over time. Normally a shield is not used as a conductor. What we do to prevent electromagnetic interference is that a lot of times we'll shield the conductor. A shield would be a piece of metal foil that's wrapped around our conductors. But this is our conductors, and what we do is we'll have a metal foil, and I'll see if I can find a picture of this. Now what we normally do to prevent this thing from acting as a conductor, because anytime you have current flow through a wire, it's going to generate a magnetic field, and also you get a voltage drop and all this other kind of things that we've got to work out. So what we want to do is we'll take this shield only on one end, and we'll connect this to earth ground. So now what it's doing is it's acting like an antenna. So what happens is when the electromagnetic waves come into the shield, it's got a low impedance path to ground, and these are true shielded cables. For some reason in fiber optic, when they started building coax cables or coaxial cables, this is a conductor, but they still refer to it as a shield. So what you got to understand is you need to use the terminology of the trade, even though the terminology of the trade is not always correct. Then what we have is we have an insulator, and this is what sets up the capacitor. And then, so this will be an insulating material. And then within the insulator, we'll have our center conductor. And this would be the coax cable. All right, single conductor, but we refer to it as a cable, of course, because it's made up of multiple layers. So that's another term that we'll use. So this is the coaxial cable, and I don't know if you can see it or not, but I'll try to swing it around, but we can see the components. So what we have to strip this is we have a special stripper. So this is a coaxial cable stripper, and the one that we got's got a slug in it. So different types of coax cables, what you can do is you can take the slug out and then change it around. What we want to do when we strip this is we want to strip it almost like this drawing right here. We want to have a section of cable coming out, we want to have a section of the insulator coming out, and then we want a section of the shield coming out. So this would be the actual strip back here. And then of course I didn't draw the outside jacket, so the outside jacket would be out here. And this can be different colors, but it's predominantly black. And what we do is it's got a little plateau on it right here, and when I come in here I lay this in, and we line it up with the tip, and then it's got a hole back here. You can see what I'm going to do is just going to take this. Now what it has is, you can't see it, it's got blades in it, and the blades are set at different lengths. And what we have is we have an Allen wrench screw right here while we're playing around with this. So whatever cable you're going to strip, once you set it for one of them, then this slug right here should be the same. So what we'll do is we'll lay this on the tip. And we've already adjusted this. So you scrap some cable while you're setting the thing up. So here's Allen wrenches right here that controls the two blades. Now once you get it set right, then this guy is not going to touch the conductor, and it's not going to touch the shield. So we just put it on there, we grab our finger, and then we just spin it around. And then when we feel it spin freely, we come over here and grab it real good, and we pull it off. And this is the way the strip cable looks. So what we have is we have the shield or the braid that comes around the side. Now I'm going to lay this back here. Now you can get this with that uses a foil, aluminum foil, that is the shield. I don't like that. I like the braided shield. And then this, you can get this with solid conductors too. So if you're doing a coaxial cable, the RG59 that comes into the cable company, it's got to use a solid strand. It's got to use a solid strand as a center conductor, because that's what it uses when it plugs in. It uses what cable TV, we use what we call an FNC connector, and we'll look a little about that. But it actually uses this to plug into the female part of the connector. So this wouldn't work on there. But this is the center, the actual center conductor is a stranded cable. This is the insulator, and then this would be our outside conductor, which we refer to as a shield. They have tools that automatically crimp this on, and we'll show y'all some of that. But this is a typical coaxial cable. And of course, the spacing, we have to maintain the spacing. So later on, when we look how to terminate this, we'll see the connectors and how we maintain this precise distance between the inside conductor and the outside conductor, and we keep the insulation at the same thickness, and that's what sets up the capacitor. So this is a typical coaxial cable, single strand coaxial cable. And when you do that, it sets up this characteristic impedance, and it's got an infinite length. So if we put what this thing's rated at, so if it's rated at 100 megahertz or something, that's when the characteristic impedance comes into play. You cannot measure the characteristic impedance of a cable with an ohm meter. So if I came up here with an ohm meter and put it between the inside conductor and the outside conductor, it's going to measure infinity, because that's a resistance. That's not an impedance. So what we'd have to do to get the characteristic impedance, if I wanted to measure it, is we would have to put a frequency on the cable, a rated frequency on the cable, and then we would measure the impedance another way, which is pretty interesting. But make sure we're not going to measure the characteristic impedance, but remember, whatever cable you're replacing or whatever system you put it into, you got to make sure you use the right cable, because each cable has a certain impedance. And if you use a different coaxial cable, even though it looks the same, if it don't have the same characteristic impedance, then you're not going to get maximum transfer, and you'll get crummy communication on your communication. The next, and these are different ones, and of course we looked at this, and these are what it's rated at in the different cables. What this next chart is, and I'll try to put this chart by itself, is it gives you the different diameters and everything of the cables. And then what's nice about this, it gives you the gauge, it gives you the diameter of the cables. What we have here is RG58U. We call it RG58, but all of them got the /U on there, and exactly what that stands for, I've looked it up before, but I'll do that with this. But we have 1, 2, 3, 4, 5 75 ohm cables. I'm sorry, RG58, and I told you wrong. RG58 is a 50 ohm cable, and RG59 is 75 ohm cable. So the RG59 is what we use, what the cable company uses. RG58 is what we used to use for network. Of course, you'll still run into that when you get into, if you ever got into actual radio transmitters. So you got to understand, when you transmit that power, that antenna has a certain impedance, and then you run the right cable to that. Then you run, then your amplifier, whatever you're transmitting on, your actual transmitter, would have that same impedance. And as long as all the impedances in the system match, then you get maximum power. Receiving RF signals is not as complicated, because all you're sticking is a wire up in the air. But transmitting RF signals, we have to make sure that we try to maintain what we call impedance matching. Used to, when we had antennas on our house to pick up broadcast TV, people would run just regular wire up there instead of running the correct 300 ohms. So the old broadcast antennas that you still see sometimes on movies that people put on their house, this was 300 ohm, and these are 300 ohm antennas. So that was the impedance on cable. So what we ran is we ran a 300 ohm cable down to our TV, and then we put that in the back of our TV. We did, and it was a duplex cable, but it was really neat because the two conductors were out, and then it had an insulator in between, which was real flat. And then, of course, the spacing between these actually established the 300 ohm worth of impedance. So now we don't use those because broadcast TV has gone up to high definition. It's at least in our area, And so now you have to have a special antenna. And what the impedance on that antenna, I'm not really sure. I'll try to find out and see. But this gives you the gauges and everything, which is pretty important. The next type of cable that we use in communication, especially in networking. In networking, we use a lot of what we refer to as twisted pair cable. And of course, what we do is we have two wires, and we use what we call differential signaling. And I need to add a little bit of that to our presentation. But this differential signaling, used to for years, what we did when we try to communicate, and this is what we do with coaxial cable, is we still come up here and reference this shield to ground. So what we do is we have two wires to send electricity. And what we usually do is we come up here and use one as common, and we usually reference that to earth ground. Well, what was happening was we were sending this signal, and this became known as single-ended. But what was happening is when we'd come over here and an electromagnetic interference would come through the wire, it would induce a wire into our signal lead, but it wouldn't induce it into the ground lead, because a signal can induce a voltage into earth ground because that's what it's looking like. So what would happen is I'll be trying to send information, and this would really show up on digital. So I'm trying to send digital information, and what would happen is we'd get a big old voltage spike in. And then, of course, if this was a digital 1 and this was a digital 0, I just screwed up because I put different packages in there. So what was going on is when we came up, now the coax cable was really good over distance because the shield was on the outside. So what would happen is when the EMF came into the shield, it would go to ground and we wouldn't have any problem. But when we try to use standard wire to send signals, which were inside computers for years, we had to really limit the length of these cables because of... So what they did, they came up with a technique that we call differential signaling. And what we do on differential signaling is we have two wires. They're usually twisted pair wires, but not necessarily, and we'll talk about why. And what they do is they come up here and don't use ground. What they do is they come over here and put a signal, and I'm going to put digital signals. And then what they do is the other signal over here will be the same signal, but it will be a mirror image of it. And so this is a symbol. So a symbol is something that we use to represent things. In math, when we see that symbol, it means add. In differential signal, if we see this thing, it means the uninverted signal. And then the minus symbol means the inverted signal. So every time you see plus and minus, don't think about DC and AC polarities. So in electricity, the plus means the positive polarity, and the minus means this symbol means the negative polarity. But in other applications, in digital, this symbol means or, and this symbol, which we use times, but we don't usually use that. We use the other symbols, which would be the dot or the parentheses, means and. So what you see is a symbol, and the symbol represents something. And these applications right here, symbols can actually mean different things. So what happens is we came out with an amplifier that we're not going to get into that we call a differential amplifier, and we bring our inverted and our unverted into a differential amplifier. And what the differential amplifier does is it allows differential signals to pass, and it blocks what we call common mode signals. Common mode signals are signals moving in the same direction. So what happens, this is called common mode. So common mode signals are signals moving in the same direction. So what happens when I come up here and have a EMI come through this, it's going to put a spike, and it's going to put a spike right there. Well, these signals are moved in the same direction, so our differential amplifier will reject these. And what it does, it allows the signal to pass, and it recombines them, and we end up with a single-ended signal that we use inside our controller. So inside your controller everything is usually single-ended, but what we're doing here, of course, is to transmit and receive data. So what we do on the twisted pair cable is differential signals. So USB is differential, universal serial bus is differential, serial ATA is differential, which is the way we interface mass storage device, hard drives and stuff to computers now. Ethernet is twisted pair. So eventually, even with Wi-Fi or wireless, eventually you got to go back to hardwired stuff. You got to wire stuff. So I can't amplify without using wires. So I might receive it, bring it in using differential, and re-amplify it. So what they do in networking is, but we still need to have characteristic impedance of this if I'm going to get impedance matching. So what they use is they use twisted pair cables. So what we have is we have two wires, and why we call them twisted pair is exactly this. They go in pairs. So this would be an example of a twisted pair cable. Now, literally, these guys are twisted together, and you don't really have any doubt. And this sets up a capacitor and inductor, capacitor between the two cables. So I've got an insulator. That's why you need to keep these twisted together. And then, of course, here the inductor is real easy to see. It's hard to see on a coaxial cable. So this is the characteristic impedance of that. Normally, twisted pair that we used in networking is a 100 ohm cable. And you're not going to measure 100 ohms between the wires, because when you measure 100 ohms, if you put an ohm meter across there, it don't see the capacitor, don't see the inductor, and all you would do, of course, you would measure infinity. If you put an ohm meter across here, then you're going to measure the R of the wire, and you're not going to measure the characteristic impedance. So characteristic impedance only comes into play when we deal with AC, or of course communications is definitely AC, or change in DC. So this is an example of twisted pair cable. We call this UTP cable, which stands for unshielded twisted pair. And this is a typical network cable, and these color codes we'll look at when we start working with these cables. But notice we have two, you can see, and the way they do on this, on networking cables, is we put a solid color wire with the same color, but it's going to be striped. And then we put a striped, but they're going to be, the stripe is going to be the same color as its matching pair. So this would be blue, white. We call this blue, white, blue, orange, white, orange, brown, white, brown, and green, white, green, white, green. Green, white would be the stripe cable. And these are twisted together. And later on, when we look at this, it's imperative that you maintain these twists into your termination and into your splicing. Because if it comes out of the twist, what you do is you by a certain length, which I think is around 1/4 inch, so it's not very much. Then what you do is you change the characteristic impedance of the cable. So then we have what we call shielded twisted pair. Shielded twisted pair, we would use shielded twisted pair in extremely high frequencies. And also we would use it in very, very electrical noisy environments. And you can see what they do. Normally on these shields, they actually use kind of like aluminum foil that we wrap around there. This would be an example where they shield the whole cable. This would be an example where they shield the cable. They shield all the conductors, and then they shield individual conductors. And then this would be an example where they just shield each individual pair. and this would be called STP, or shielded twisted pair. These are not exactly right. The actual distance on all these cables is 100 meters, which would be roughly 330 feet. Now, this is for the cable. What we would have to do is, if we're going to go over 300 feet, then we would have to run it through some type of amplifier, or some type of, sometimes they call these repeaters. We'd have to run it through some type of repeater or some type of amplifier. But we could go through a repeater. Could be what we call a switch. It could be a hub. It could be all different types of things. A router. Most of you have heard of routers, and we don't have time. I don't know if we have time to get into some of the terminology of networking. We might do that. And of course, this compares fiber, and this is in meters. So something called the multimode, and we'll look at this later on, has a length of about 2,000 meters, and this is glass. Most of your plastic, I don't know of any. We have what we call stepped index plastic, so it's usually limited to around 100 meters, but still 100 meters is 330 feet. This is a little better. So what we do is, similar to meters, what they've done is they set up different categories of networking cables, of Ethernet cables. And the current cables that we use are called the 5E, the Cat6, and the Cat7 cables. What we have run here at the college, we have the 5E. I don't know if we got any 6 or not. And what this does is actually gives you the number of megahertz, not megabits, but megahertz that we can transfer on that. And then it gives you the voltage DC, but very seldom do we use these cables to handle DC. And then we can get Cat5 and unshielded twist. We can get it in unshielded or shielded. We can get this in unshielded or shielded. And here, Cat7 is going to be shielded. So Cat5 is used in Ethernet or any other types of data. Cat6 is used in Ethernet or other types of data. Cat7 would be is usually used by the telephone company to get your T1, T3 lines that we communicate information over using twisted pair cable, right below fiber. So Cat7 is basically the highest rated frequency, up to a 100 megahertz augmented and 600 megahertz. So this is what the phone company uses to send mostly computer information or telecommunication information over their wired network. Now, when we get into the jacket, we have different ratings that's going to be out on the outside jacket. Now, remember, the outside jacket is in there to protect the cable from the environment. So we talked about what the plenum is. So anytime we have a suspended ceiling, the plenum is going to be the space between the suspended ceiling and the actual ceiling. And this is we call this the plenum. Originally, it was given the name as a plenum because it was used for the return for a lot of air conditioning systems. So even though our air conditioning system here at the college does not use the plenum as the return, as far as I know, it may. But normally when we in a building like this is where all your networking cables end up being run. Especially if you look at our campus, because we have cinder block walls over in the hall building, and cinder block walls are really hard to get stuff through. So normally we run our network cables up through the plenum. But to run in the plenum, anytime we have fires, what normally happens is that the fire moves up, right? So when we get up there and we start burning a lot of these jackets, that gives us the protection. Then what they do is they actually put out gases that are very, very dangerous. Also, a lot of your insulations will burn a long time. So what we've got is that this guy will extinguish real fast, and it produces less smokes and fumes that are not toxic, right? Riser, these are cables basically that would be hard-drawn wires, but what these cables do gives us the ability to run them up without suspending them, and these have links too. We'll look at those. I think that's in one of our next slides where we can look at the actual length we can run a riser rated cable without supporting it with some type of clamp or something like that. Uses in vertical tray applications such as cable runs between floors, through cable risers, or in elevator shafts. These spaces cannot be used for environmental air, which what the plenum is. These cables must self-extinguish and must also prevent flames from traveling up the cable in a vertical burn. So these are your riser cables. So CM, these are your designators. R, riser. P, these are pretty straightforward. CMP, if that's on the outside jacket, that's going to be a plenum rated cable. CR, CMR would be a riser rated cable. Then we have our general purpose cables. These would be CM without the G, CMG, of course, which is pretty in CMX. And these are Universal Laboratories have tested these, and this is the test that they ran on it. Will burn and partially self-extinguish, not for use between floors or in the plenum space. Often these cables are used for workstation cables and patch cord. So the cable that we've got, and I don't know if I've got, unfortunately when I ran it, I didn't get any of the markings on the cable. And I need to go and get those. But all these are going to be out on the outside jacket, what the jacket is rated at, what the cable is rated at, what type of cable it is. So we'll look at that later on. These are actually a really, really good one. So CMP, we can use these for communication. CMR, CMG, CMX, and CM and CMX. These are all would be used for communication cables. The CL, these are your class 2 and class 3 remote control signaling and power limited cables. FP, these are going to be fire alarm cables. CAT, these are going to be your communication tables for your television and your radio. 0FNP, these are going to be your, so OF, those are pretty opposite, is optical fiber. These are going to be all your different fiber optic cables. PLTC, these are going to be power limited, and then BMR, these are going to be powered network powered broadband communication cables. So supposedly, if you're going to send power through some of the wires, Ethernet, by the way, only uses we use 8-pair cable, 4-pair twisted pair cable, but Ethernet only uses 2 of the pairs. So what that does is that gives us 2 other pairs that we can use for other things. But what we have to understand, if we send power through that cable, then we're supposed to use a PMR or a PM rated cable for power for those cables. What they did here at the college, I'm not really sure, but when we originally had our phone system, it was a hardwired phone system, and we ran individual wires to every phone, and you're still going to run into that. But what we went over to something called voice over IP, which means you send your phone through your network cables. Well, unfortunately, these phones have to be powered. These phones have to be powered up. So what they did is they're sending power through the network cables. Now, whether they're using the BM rated cables or the BL rated cables, I don't know. So CMP, we know these are so CM, these are communication. OF, these are fiber. And then OFCP or OFC, these are going to be fiber with a metallic or conductors or electrical conductors in there. So STP, and I've got STP, which would be shielded, STP, UTP. This would be running an outside shield, but the individual connectors are shielded. UTP, 4-conductor, and we'll look at these. These are not 4 these are 4 pairs. This is what we primarily use in Ethernet or wired networks. We'll get a brief look at fiber here. Just a very brief look. So what we got on fiber, the typical construction of fiber is of a fiber conductor is we're going to have an outside jacket, and then we're going to have an Armistead coating, which they're calling Kevlar here, but Kevlar is a registered trademark. So there's a lot of companies that's making this Armistead or very high strength fiber, that is not Kevlar. Then we have a go-between, which we call a buffer coating. And this is not quite true. Normally what we do is around the buffer coating, we're going to have some type of jacket. And we'll talk about this in a minute. So I'm going to draw a jacket around here. And then what we have is we have a plastic coating around the outside, which we refer to as a buffer coating. A lot of people just call it the coating, though. Both of those are perfectly legal. And this is to add strength to the glass. And then we have the actual fiber conductor itself. So we give these things a lot of support. Then we have what we call a duplex cable. So the duplex cable is going to be split. It's going to let you split it. And then these right here contain two fibers. And then we'll still have the Kevlar. We'll still have the buffer coating, also called a buffer tube. But here we'll come out. We'll be able to bring these two cables out. And normally there'll be two different colors. I'm going to give them the two different colors. And I think it's actually orange and blue, but we'll look at those. Then we have what we call what we call loose tube. Normally we use this inside. We use tight buffered. So this is actually called tight buffered or tight tube. In tight tube, what we have is that your tight buffer is actually in contact with the buffer coating. Then we have what we call loose tube or loose buffer, which means they have this outside buffer will come up and we'll have a tube, and then the fiber comes running out of that. So the fiber actually runs loose inside the buffer. We usually use this underground where you're going to have a lot of stretching and moving around. Any type of really mechanically noisy environments where we have a lot of vibration, a lot of shaking, a lot of stress where things move around, then we'll use loose tube. Inside the building, we'll use what they call tight tube or tight buffered, and inside the building. And what they'll do, we run this underground, and what they'll do is they'll have a gel inside this thing to prevent moisture from getting inside the cable. And of course, when you splice these, you got to get rid of the loose tube. One thing that you got to get rid of is that gel. I'll clean it off. So this would be one of the things that I made. It gives you an example of tight buffered and loose buffered. So this right here would actually be the coating. And then this right here would actually be the conductor. And then this right here would be the tight buffer or the tight tube. I usually call it a tight buffer. But if you look up on the internet, you type in tight buffer or tight tube, they'll come up and give you the same thing. This would be loose tube. So this right here is the coating. And then this right here is the conductor, and we'll look at the parts here in a second. But like I said, this is just an introduction. And then, of course, and then this would be the loose tube or buffer. And inside here, what we'd usually have is we'd usually have a gel, especially if it's going to be an outside cable. If you're going to use loose tube inside, you usually don't have that gel inside there. But if it's going to go underground or you're going to run it outside, I guarantee you they're going to have that. And this would be an example of a duplex tight buffered cable. Then the book talks a little bit about a breakout cable. This is where we have multiple conductors inside a table. Normally what we have in here, we have some type of strength member. This is usually going to be a Teflon tube So when we pull this, we're gonna pull with that strength member. And then of course, this would be our outside jacket or outside buffer. And this would be our Kevlar or our Armistead. Then this right here would be our conductor. And it looks like this is a type. This looks like this is a type tube or type buffer. But what we do is we have multiple cables. So what we have inside a breakout cable, we would have 6 conductors. And when we get into fiber optics, we'll look at different methods that they use, different arrangements that they use to bring these fiber in. That's the end of this lecture. But what you're going to have to do is you're going to have to watch the rest of this. So I'll start another lecture and give it another title. And I'm going to upload both of these, and you're going to be responsible for both of these before next week, watching both of these. And I'm going to put an online topic quiz on there also for these too. So watch out for those.